So good afternoon, everyone, and welcome to today's RGU Knowledge Bites for Business webinar. Today's is HyRISE, Overcoming the Risks. My name is Neil Farman, and I'm the Net Zero Business Development Manager here at RGU. Before we get started with today's discussion, just wanted to briefly draw attention to our housekeeping slide to make sure we all have an enjoyable session today. So I'm sure this is all now the standard webinar rules that we're all come accustomed to, but I just really want to highlight that the key thing is that we'll welcome your questions throughout the webinar, ask them, post them using the Q&A function at the bottom of your screen, and we'll try and get through as many as we can at the end of the presentation. So I'm sure, as most of you all know, over the past year, Knowledge Bites for Business webinars have considered critical current and future challenges across a number of industries. So with COP26 fast approaching, our experts are now tackling some of the key barriers in the transition towards net zero with our Runway to COP26 Knowledge Bites for Business mini-series. Hydrogen is currently a hot topic of discussion in the energy industry, and I'm delighted to say that we are joined this afternoon by Dr. Nadimul Faisal, who will be sharing insights into some of the methods to support the acceleration of hydrogen and how we can overcome some of the associated risks. So without any further ado, over to you, Faisal.
Thank you, Neil. Thank you very much. I'm Nadimul Faisal. I'm a reader in mechanical engineering at RGU. My area of interest is surface engineering and micromechanics, in particular thermal spray coatings. So in today's presentation, I'll be talking about giving high-level information about hydrogen production, what are the state of the art, then moving on to electrolysis and what are different type of electrolyzers, look into the materials aspect, because materials is the main part of my presentation today, and how you manufacture, what are the techniques available, and in particular I'll touch upon using thermal spray technique. And the last part of my presentation will be about the risk and what we can look into, what could be the future direction or what we should be looking into. Right, so before I move on to my presentation, I would like to acknowledge my collaborators, partners, sponsors, colleagues. These are my colleagues and partners who have collaborated with me, or I have collaborated with them related to thermal spray coating. So I started my journey in thermal spray in 2001, working at ARCI in India. A number of colleagues I worked with, I learned some of the fundamentals. Later on, I moved on to Hiriatwat doing my PhD, thermal spray coating. Then I had chance to collaborate with a number of academic partners, companies, developing solutions using thermal spray technique. Right, so currently we are all aware of the shortages of gas in the UK and other places as well. And it is in the news very frequently. So hydrogen is one of the gas. So I thought to just touch upon that, what is happening currently. So as per the news, we all know that post-COVID, a sudden rise in demand, economy is rising, so there are business going on. And the gas demand has increased worldwide. Winter is coming. There are some issues in the power grids. And there are news that nuclear power may not be available in winter. And some of the maintenance may be happening in North Sea. And the wholesale price is rising. So combination of all these factors has led to a shortage of gas in the UK. There may be other factors as well, and these are very complicated things to pinpoint one good reason. Right, focusing on hydrogen today, what are UK government plans? The plan is very straightforward, that hydrogen has to be made as safe as natural gas. And they have planned that it has to be used in larger scale. It has to be stored, distributed in a safe way. And by 2035, the plan is that hydrogen will make a significant role in our economy, like people's home, businesses, cars, cookers, boilers, and many other applications. So there are a lot of things going on, and we have our role to play. Now, in Scotland, the plan is that there will be about 5 gigawatt of low carbon hydrogen production in Scotland in 8 years from now. I would say that's ambitious, and it is possible to have 5 gigawatt of hydrogen production by 2030. So how it will happen? A lot of things we have to look into today. So I'll touch upon hydrogen projects worldwide, what are production, storage, transportation, and cost factors. And how about do we have current resources where things are? Now, worldwide, there are about 197 projects ongoing in the last many years. And you will find most of the hydrogen production related projects is focused in the States and Europe, some in East Asia, a few in Southern Asia and Middle East. How about UK? In UK, there are a few projects, and there are a couple of information here, one coming from the Google resources. There are a number of about 12 or so projects going on. However, if you see current UK hydrogen strategy document, you will find that they have planned about 5 megawatt electrolytic production project and 5 megawatt electrolytic production projects over 5 megawatt. So if you combine all these together, you will find that the total is 110 megawatt, which is as per the current planning. So a lot of hydrogen will be produced over next many years. Now we are in Aberdeen, so Aberdeen, you would know that a pioneer in using hydrogen in transport in Europe. So what happens in this case, you get hydrogen, you fill these tanks on the rear side of a car or a bus, and then you use this hydrogen as a fuel to power up the fuel cell. And you can see some of the data here that about 26 kilogram of hydrogen, 20 kg of hydrogen every day needed per bus. And it takes about 10 minutes, 9 minutes to refill at 350 bar. And with that 20 kg of hydrogen, you can travel 190 miles. Right, so think about the storage location, think about how you will convert that fuel to power up the fuel cell, hydrogen fuel cell, and that can be used to power up the machine, and that is how the automobile works. And there are many other accessories around. Now, if we just focus on the transport sector, and this is data taken from the government source, you can see that over years, how many miles we drive in UK. So this is combined data. You'll find that because of COVID last year, the data has gone down, but it is over 350 billion miles we drive. So I did some calculation which are in the gray color. I don't want to talk about those. But the high level information which I came across is that we need, if we have to convert today all transport sector into green, means using hydrogen, then we have to produce 16 million kilogram of hydrogen every day. And assuming that 350 billion miles is driven every year. So we need to produce about 8.5 times more compared to current overall rate to meet the current demand in transport sector in the UK. So you would know that currently hydrogen is produced using other method like methane reforming process, which is not green method. So I'm talking about using green method. So you really have to scale up the production. So a huge demand. Can we meet those? Or what are things we have to do over time? Now, some basics, some fundamentals of facts and numbers about hydrogen. So hydrogen is colorless, we know, odorless, tasteless, and non-toxic gas. However, it disperses very quickly. It is nearly 4 times as fast as natural gas. and it has the highest energy per mass, like 143 megajoule per kg. And 1 kg of hydrogen has the same energy content as 1 gallon or 3.2 kilogram of gasoline. Now, one of the data which is important here is the higher heating value, which is 39.41 kilowatt hour per kg for hydrogen. This is a number which is very useful to do a lot of calculation to come up with how much production is needed and so on. Now, economy-wise, everybody would want to reduce the cost of hydrogen per kg. So currently, according to some estimate, is about 10 kg. It may be higher, it may be lower. It depends how you are producing it. However, this need to be go down if we have to use it in larger scale in the economy. Now, what are different hydrogen production methods? Historically, fossil fuels are the most common one, where you have got hydrocarbon reforming. But it comes with a range of byproducts, in particular carbon dioxide, which is not wanted. However, in current times, over last 10 years or so, renewable energy have been used. Some of those you can see listed here, like biomass process, within that biological, Photolysis, fermentation, and then thermochemical process like pyrolysis. And in bracket, you will find those percentage, the efficiencies or so. However, today I'll be talking about the water splitting and how you can use that using electrolysis technique. However, currently it comes with a high capital cost. Initial investment could be high, but over long term, it can be better. Currently, 95% of total production is coming from steam methane reforming, and the rest is coming from about 4% as green from from electrolysis process. How about the storage method? Means what are different techniques? So the gaseous form is the most mature form. You can store these things in a storage tank. However, to store it, you need to compress the hydrogen at a given pressure in a container, a pressure vessel. So a lot of work is needed if you're thinking about hydrogen economy. If a larger scale production happening in various parts of the country, you need to have a good compressor, a cost-effective one, which can compress to a high pressure in pressure vessel. And then you can do in liquid form, which is cryogenic. Then you can do adsorption on carbon nanotubes, adsorption to form hydrides and complex hydrides. So those are some of the material used if you are storing in hydride form. However, the most common one, as I said, it is gaseous form. It can be used in automobile easily. And the cryogenic requires a lot of energy. So there are a lot of opportunities here in terms of innovation. In terms of storage, you can see on the right top screen, these are some of the pressure vessels we have designed in our group led by Professor James Juguna. This is lightweight, a small module. At the bottom, you can see the number of standards available, about 34 ISO standard directly related to hydrogen technologies. So from my assessment, I see the other standards are needed as well if you are talking about hydrogen economy. In terms of hydrogen transportation, you can transport using pipeline or truck, the compressed gas form or liquefied form. However, it all comes with advantage and disadvantage. The stainless steel, the first one, like a pipeline, is very common one. It comes with issues like hydrogen embrittlement. However, aluminum and copper are other materials, but it has got other disadvantage, mainly the strength of the pipeline itself. Now, in a recent report by OGTC, or currently Net Zero Technology Center, it was suggested that about 40% of the pipelines can be suitable for hydrogen transportation. Now, if you're using the existing resources, so the pipeline may not be as strong as new, so it will have some residual strength. So you have to think about it, designing or putting a pressure in such pipeline which can sustain and transport it safely. So there's a lot of work can be done in that area, how you can use the existing infrastructure in North Sea to transport hydrogen. There are opportunities to develop a larger scale container or cylinder which can store hydrogen at high pressure and be able to go from point A to point B. And especially if you the opportunity to manufacture composite lightweight HDB container. Okay, however, in all these process, you always lose some of the hydrogen. And that is not good for the environment as well. I'll talk briefly later on that we need to store it, contain it ethically, so that it doesn't harm the environment. Now, how about the current status? Right now, we have got about 11 refueling stations in the UK. However, if you compare that with the petrol stations in the UK, it is about over 8,000. If you take the ratio of these numbers, you come up with about roughly nearly about 800. So that is how we have to do if you want to convert the entire economy just on refueling purpose. So it's a huge demand I see. And you can see these are some of the companies who have taken initiative, investing on it, and doing things in the right direction. And luckily we are in Aberdeen, so you can see you have got two filling station, which is amazing. Now that was the high-level information about hydrogen. Now is the electrolysis and electrolyzer types. Now, if you see the future, that what will happen over next few years. So this is the capacity additions per year. You can see that the global electrolysis capacity is becoming bigger and bigger. Well, this data include the historical data and those which has been announced in megawatt per year. And within these numbers, you will find that 110 megawatt, which has been planned by the Scottish and UK government combined. So that's quite a big number. However, there are many other countries who will be investing on such infrastructure. So that number is something we have to look into. Now, moving on to electrolyzer or electrolysis. So what you need a material and manufacturing process. So you need a catalyst type of material. Then you need a feedstock like water, electricity, heat, sunlight. You are thinking about zero carbon footprint, so you would like to have electricity from renewable energy sources. For example, wind turbine. Then you need to combine with these material with water. Then the breakdown will happen. You can produce hydrogen. Then you can store it in a gaseous form or liquid form. You can compress in those forms. You can store in those forms. You can transport in those forms. And then how about the usage? So you can use in transport, industry, energy storage, or various household. So that is a simple block diagram if we are looking into electrolysis process and the green hydrogen. Just a little bit digging into what is electrolysis. So we know that it was found by Michael Faraday in 1883. So this is focused on like Faraday's laws of electrolysis. It is related to chemical change, related to current at the electrolyte layer. So if you've got electrolyte here and electrode here, so what is happening at the interface, and the electricity and the equivalent weight of the material. So it is to do with the feedstock, means feedstock around, and the material of the membrane itself or the electrode itself. So this is a very important, fundamental for any electrolysis process. And you need requires at least 285.8 kilojoule of energy to split a mole of liquid water to produce a mole of hydrogen at 25 degrees centigrade. So that is a number. You can use that number to calculate number of things. And then you can calculate the efficiency and how much voltage is needed. That is 1.481 to split liquid water into hydrogen and oxygen. So there are a lot of analytical calculation is required. Now, if I categorize various type of electrolyzer, you can see the top three is based on water and electricity. First one is proton exchange membrane type. Second one is an anion exchange membrane. The third one is alkaline water electrolysis. And then moving into next type, which is water with heat and electricity, and without electricity, those are SOWE or solid oxide, you call it. Then you have got thermochemical, which is largely based on which is largely can be done at nuclear power plants. Then you have got water and sunlight, the two types within the two types of it, photolysis and photoelectrochemical method. So based on the feedstock, you can have different type of technologies, but overall you need water, electricity, sunlight, and heat, as well as the material, and you can split water, and then you can produce hydrogen. However, these are the current state of the art. There are opportunities to come up with an innovative idea where you can have a different combination of these feedstock, and you can produce hydrogen from clean water or wastewater or something else of those type. Now, digging a little bit deep within those electrolyzers, so I'll spend some time here. So a simple electrolyzer PEM type looks like this. It has got a membrane. It has got electrodes, anode and cathode on either side, and it comes with a bipolar plates, and it comes with a porous transport layer. And again, on the other side, you have got bipolar plates, you have got porous transport layer and anode. And these are physical materials. What are they? So in bracket, I put some details here, some of the more commonly used material. And it comes with some features, functional features like catalyst layer. It provides path for proton transport, network for gaseous reactant supply and water removal. Bipolar plates, it provides it acts as electric current collection, heat removal, gaseous reactant distribution, and so on. And similarly, a gas diffusion layer, microporous layer, they provide a mechanical support as well as passage for reactant supply. So there are a lot of materials, and everything comes down to those materials, which is listed here, and some I will show you later on. So if there is no material, you cannot produce hydrogen from water. So you need catalyst, electrodes. This is another type, which is an ion exchange membrane type. Again, overall, it looks very similar, but the operation-wise, it can be different. In all these cases, here I have drawn a schematic diagram. On the left side, you can see where you can use various thermally spread layer to design and manufacture your catalyst or electrodes. This is a solid oxide water electrolysis type, where you have got which operates at very high temperature. And then you have got alkaline water electrolysis. Again, it requires various material, different design as well. Then you have got photolysis, where you can use sunlight in a given spectrum. The spectrum will be ultraviolet, visible, or infrared. So you need these many energy or photons, which can help the material or catalyst to split the hydrogen. Other spectrum is too low to do anything on such material. It requires some other design. In terms of thermochemical, as I mentioned, this requires very high temperature. It means water need to be heated to up to 2500 degrees centigrade. If you are using your electrolyzer at that temperature, you need to have different material, mainly refractory materials, ceramic or high temperature alloys. So there are a good example, but not many. Most of the work has been done in Canada. However, in UK, the government is planning to look into or develop such technology over next 20 years. Then this is the last one, which is photoelectrochemical. You need a combination of electrolyte and sunlight to produce a split water into hydrogen. Recently is very recent one. There are two other technique which has come up, which is supercritical solution or HyRISE, which is using untreated seawater to split water into hydrogen. Now, if you're looking into thermal spray material, which can be used for photolysis application, you can see some can be in solar selective range, some can be photocatalytic one, and some can be in thermal barrier range. And those are the common material like metal oxide, zinc oxide, titanium oxide, nickel molybdenum, tungsten carbide, and titanium oxide, and YZ, yttrium stabilized zirconia. So these are typical or common material used through found through different literature. There are many other things can be done in different spectrum, but as I said, the photon energy is too low to do that. However, in future, if some material can be developed, then potentially you can use microwave as well, or millimeter wave. We don't know yet. Now, looking into the efficiency of the electrolyzer. So these are, you can see in column 4, the typical efficiencies. But PEM, like proton exchange membrane, that is a technology which is very common in the industry. That is the main technology currently. However, other technique like alkaline one is picking up. Solid oxide can be useful at high temperature. Thermochemical can be useful in nuclear power plants. And other techniques is related to do photolysis or photoelectrochemical techniques. So each comes with advantage and disadvantage, limitation. Right, let's go into the material aspect. Now we all know periodic table. Each element has their importance, but which part of this periodic table is important for electrolysis purpose? You will find that means through some analysis and literature, I came across that for each category of electrolyzer, the typical material which I have listed earlier, some here, you'll find that for proton exchange membrane, titanium, which can be thermally sprayed, are used on bipolar plates. Anion exchange membrane, nickel, aluminum, molybdenum for cathode and anode, and so on. So the list of materials which are used in different parts within those electrode or chamber. Now, all these are part of the family of this different family, other S, P, D, F shell, where you are. So you will find that most of the material is coming from transition metal groups, so in between here. And this can form a combination with other groups as well. So, but literature-wise, I found that those material which are hidden is used for electrolysis application. So typically more than 27, there may be a few more, I believe. So those materials, and they are transition metals and some alkali metals, and it has got some features or functions. You would know that transition metals are used as catalysts. They are good conductor of heat and electricity, and easy to manufacture, high density, and so on. And alkali metals, they are soft and not dense. So there's a combination of elements which can be used to manufacture materials. Now, where are they found? They are found in various countries. Those in the red color I've highlighted here, those are the critical ones, important ones. Those other color, which they may be a new material. But again, we need to mine all these material to manufacture the electrodes for electrolysis. So the access to these material ethically is very important. Now, going into how thermal spray can be used to manufacture various catalyst electrode layers. There are different manufacturing routes like deposition, rolling of foils, pressing and heating, sintering, thin film deposition, and thermal spray. So thermal spray is my area, and I'll talk to you about that, giving some of my example I've done before. What is thermal spray? So in this case, you spray feedstock material like wire or powder form. Powder can be of various types: ceramic, metals, polymers. The industry is very big. It's going to be about 11 billion in 3-4 years. In this case, what you do, you have a pressurized gas or a liquid form. You spray through a nozzle or gun on a substrate. And there are different type of thermal spray technique. On the right side of the screen, you can see combustion type using electrical technique or cold spray technique. The advantage of having such technique is that you can scale up the manufacturing very easily. And these are industrial technique. I'm not talking about the laboratory based. These can be used in laboratory, but these are the industrial technique, which we all use it, but we don't know where it is used. It is used in aerospace sector, automotive, healthcare, agriculture, and so on. This is an example where we are manufacturing electrode for anode application. What happens in a sprayed particle goes and sit on the substrate at very high speed, at high temperature. Most of the time, it depends on the technique you are using, and it forms a mechanical interlock with the rough surface. And with the control on the process parameter, like what distance the gun should be, what should be the velocity, what material, and so on. There are about 6-7 types of process parameter which can be looked into to design the coating or electrode you want to develop. So you can control the porosity, you can control the thickness, you can control the roughness. So the number of things can be done from this technique. So on the left side, you can see this is a feedstock powder material, ceramic powder. When it's sprayed through the flame, that is how the partially molten surface looks like. And when it lands on the surface, it breaks down and forms microstructure. This is a cross-section, unpolished version of an alumina. You can see that how the powder, when it's sprayed layer by layer, you have got a very distinct features. This is microscopic, and this is a nanometric powder used. So different technique used, microstructure looks very similar. Now you can see on the right side of the screen, these are different electrode surface using different materials, mainly molybdenum carbide with different metal oxide. We have using plasma technique, where we control various microstructure. We wanted to have high porosity in this case of thickness about 300 micron or less. On the left side, we have got some resources which we use it to characterize such electrode materials. Right. Now, again, going back to those 7 electrolysis technique, and you can use various technique like vacuum plasma spray, atmospheric plasma spray. So you cannot use just one technique. Different material requires different processing technique. And within thermal spray, there are a number of techniques. So you have got a range of options, a range of material which can be applied to manufacture various electrode or catalyst layer for electrolysis application. Now, this is a new design which we have done recently during lockdown, and some work was done just before lockdown. So we published some work. So where you can enhance the surface area of the catalyst using a technique called metamaterial manufacturing, where you can have blocks of coatings. So by doing so, if it is full layer, you will not have those additional layers in every building blocks. So by doing so, you can enhance the surface area. It means you can enhance the catalytic reaction, means you can enhance the hydrogen production. Now we need to have a very strong structurally integral electrode. So this is one technique which we used. We have got a high strength alloy, Hester alloy, and we did a coating on one side and compressed along this direction. And we put a strain gauges, and we wanted to know that what strength, what load it will fail. So by putting a strain gauge, we were able to identify how strong these catalysts can be using the technique we deployed. So that was destructive testing. Here we did some non-destructive testing where we used the neutron diffraction technique at Rutherford lab. And you can see that this is the interface, and here interface, there is a huge mismatch of the strain, but this is within the safe limit. These are the normalized residual stress. You will find that the through thickness anode layer, the strain changes is not one number. But however, at the interface, now think about you putting this one in corrosive environment in water, and you apply voltage, and you use any catalyst electrolytes. So that is very extreme scenario. So you need to sustain all these coating with the substrate for a longer period of time. So we need to do more fundamental analysis, including these strain analysis, to come up with a better design of membranes. Right. Those were a few of my examples which I've done over the last few years. So eventually, once you have manufactured, then you have to look into the degradation. If it degrades very quickly, then that is unwanted. It will be huge economic loss, because those are important materials you can't keep using all the time. So it needs to be water resistant, like less corrosion, and the thermal degradation should be less under heat or sunlight. Because of voltage, the material should not break down, or if the electrolyzer is used in a static or dynamic loading condition, so you need to look into the mechanical integrity, and then tribological behavior like crack, delamination, wear, and so on. And then electrochemical attack, like radical attack, voltage. So all these factors have to be looked into when you're designing an electrolyzer. And the last few slides, how about the risk and the future? Right, the risk, as I said, can be related to access to materials, because the range of materials, about over 27 material can we have access to, how expensive it can be. Can we have a consistent access to those material to manufacture? Because the demand will rise, but the production will not be the same pitch. So if the production goes down, then there are issues. It's a risky business. So we have to look into using those material which is readily available or can be used, and then look into the larger scale manufacturing, not lab scale. Large scale means very fast and can be done in a few minutes, a large surface area deposition. So I've just given one example using thermal spray technique. How about the feedstock? Well, we have got water in finite resources like seawater, which can be alkaline. If the rock breaks down, producing sodium, magnesium, calcium, and so on. Electricity, as people are saying that you can use a wind turbine electricity. You can use heat and sunlight is a huge resource, which we don't use much in the northern part of the globe. So a lot of things can be looked into, but however, we have to make sure those are consistent. And then how about the leakage? Once you produce hydrogen, it will go through various forms and shape and process. And make sure we don't allow it to leak, because it can have a negative impact. One of the negative impact is that it will stop cleaning our atmosphere if we release a lot of hydrogen into the atmosphere. Right, so hydrogen leakage is one of the important thing. We need to look into various protocols or standards because it is a very low viscosity and it is very difficult. Now, when you do pressure testing of any pressure vessel, you test using nitrogen gas. However, when you want to use the pressure vessel, you are using it for hydrogen storage purpose. So you test using nitrogen, but you're storing hydrogen, and you know hydrogen is a very small molecule. So it may leak through flanges, seals, and gasket. So we need to look into developing a more advanced version of the protocols or monitoring techniques so that you can reduce the leakage. Now, there are only few.
I just want to give you a quick time notice.
Yeah, thank you. Just a few more minutes. There are only 3 standards currently directly related to electrolysis. However, from my assessment, I see that the number of other type of protocols and standards for integrity monitoring, maintenance, and the repair of electrolyzers are needed if you are looking for hydrogen economy in future. Now, to sum up, like materials for enhanced functional properties will be needed, and these are a few categories of materials like metals, metal alloys. High entropy alloys have not been used yet in large scale. There can be metal oxide, a rare earth element. There are only 1 or 2 examples which has been used. Polymers, semiconducting oxides, ceramics, and carbides, those are mostly used materials as a feedstock for electrolysis. So my assessment is combination of these materials can be used for future generation electrolyzer. How about the data? We need to make a decision based on the data. So machine learning, we all know that is very useful. It can be used for performance prediction, material selection, and durability. It will help reduce the cost as well as improve durability. And it will also help understand some of the fundamentals about materials and mechanics of those things, if you look into the deep learning side of the artificial intelligence. How about the future? So we need to scale up the production. We need to look into the compression mechanism or compressor design. We need to store in the larger scale. We have to start using on transportation purpose because that is one of the big market apart from industry. Then you have to use and minimize the leakage. And there are a number of examples here like offshore asset, subsea asset, seashore assets, airspace. Airspace we don't use much. On aeroplanes, if you're flying at 40,000 feet high, the quality of sunlight is very good. Can we use sunlight to produce hydrogen on aeroplane? We can also look into some of the decommissioned asset, either submarine or subsea pipeline. You would know that submarine, historically they use PEM electrolyzer to produce oxygen, and they disperse the hydrogen to water or add to some the compound. Can we use submarine to store hydrogen? Maybe not so deep, maybe shallow water. So combination of these things, there looks like some opportunity up there. And the last slide, that we need to think innovatively. A lot of things we can do. We can look into materials, sustainable materials, abundant feedstock. We need to make decisions based on the data. We need to have an optimal design, reduce the cell mass, reduce the cost, and then enhancing the working life of these electrodes, and then look into all ethical, legal, geopolitical issues, if any, to have a desirable hydrogen production from electrolysis. Thank you.
Thanks so much for that fascinating presentation, Faisal. Really appreciated it, and it was really insightful into the infrastructure of hydrogen, how there is ways to optimize the process and really accelerate the hydrogen economy. So I'll just take this moment to remind everyone, please do, if you have any burning questions, to pop them into the Q&A set function at the bottom of the screen. So we do have one question in the chat box just now, but I think before we go into that, I'll just start off. So one thing I was quite interested about was the fact that you mentioned that this would reduce the capital costs, the thermal spray coating will reduce the capital costs. I was just wondering if with the thermal spray coatings there was going to be any associated operational costs or increased costs in that way.
Can you repeat, Neil? Sorry, I missed your question.
Sorry, no, I was just saying, so you mentioned within the presentation that the thermal spray coating process would reduce the capital costs of the hydrogen infrastructure. I was just wondering if there was associated costs on the operational side of utilising that process.
Yeah, so thermal spray coating, it is an industrial facility, so you need a workshop type, a typical large room size facility, first of all, to deposit the coating, because it comes with a lot of accessories. But once that is the initial cost. However, once you have it, then you can deposit a range of materials based on the type of thermal spray coating you are using to manufacture electrode. Now, the good thing with this is you can scale up on a very large surface area. Now, it depends what surface you are referring to. If you want to coat a turbine blade, which may be 100 feet or more, if you have got a space or booth where you can move the turbine blade, then you can spray entire turbine blade. It depends on the space you have got behind the gun. But the gun will be spraying, it has got a nozzle size. It comes with a finite nozzle size because you have to maintain certain velocity and speed and so on. So that is doable. You can scale up. And by doing so, you can reduce the cost if you are producing large scale. But for a small test coupons, for lab based, it may be expensive.
Thank you for that. So we do have a question here. So do you think the coating method you're using is applicable to pipelines and other transportation areas to reduce leak paths over just the electrolyzer?
Yes, so from some of my recent work, I've seen that the thermal spray technique can be used as a sealing layer to seal wherever you find that the leakage could happen in the electrolyzer you're after. So in one of the slides I've shown you, there is some material which is there, which can be used to seal a sealing purpose.
Thank you. What happens with impurities, for example, minerals, in the water during electrolysis? Can electrolysis be used to produce minerals from water as a byproduct? Can the impurities impact on corrosion or form deposits that impact on the system is another question in the.
So there are two types of impurities. One is the feedstock, means water itself. It is impure. The reaction will change. And if the material you are using for electrodes or membranes, if they are not pure, then it will further affect the photolysis, electrolysis process. So purity is always good. But if you're looking into large scale production of hydrogen, you have to trade off what you want. You want a sustainable design, which is very strong, can go for, even though it is efficiency is less. Or you want very high purity design, so the cost will go up. So there is a trade-off. You have to look into various elements in electrolyzer design.
I think we want to just touch back on the previous question, on the theme of the other opportunities there are with the coating method. And so one of the, this presentation was focused on the electrolyzer aspect. But do you think that there's areas such as in steam methane reforming for blue hydrogen that there is scope for utilization of thermal spray coating, whether it's process, whether it's this one or another?
Yes, so thermal spray, as I said, it is used in every sector. It is used in turbine blade, aerospace turbine blade. So where high temperature is there, you can use it. So in steam reforming process, you know that it operates at very high temperature. huge amount of carbon dioxide is released. So wherever you have got high temperature, if you want to protect your asset, you can use refractory materials to deposit on the surface so that your substrate is protected. Otherwise, you have to replace your substrate very often. So that is one application of the coating. You would know that the liner of an automobile in the engine, they are coated with a specialized material. I know about one material, alumina material. The example I've shown you, that is protected. You're protecting your liner cylinder. If you don't have such coating, you cannot drive your automobile continuously for 100 miles or 200 miles or maybe 1,000 miles. 30, 40 years ago, every 100 miles you have to stop so that you have to cool down your engine. So these things are possible because of such modern coatings.
Okay, great, thank you. And you started the presentation with a really good overview of hydrogen in the UK and worldwide at the moment. One thing that stuck out really was the infrastructure difference between sort of hydrogen. You gave that really good comparison between hydrogen and charging stations and the number of petrol stations in the UK. And you also focused a little bit on the cost of hydrogen. How do you think the sort of your thermal spray coating process has any, if it does, relation to being able to grow the infrastructure and reducing those capital costs of hydrogen?
Yes, see, if you are using PEM, they use platinum and other materials. However, to bring in additional functionalities to enhance the efficiency of electrolyzer like PEM electrolyzer, without spending too much on the electrode as a bulk material, you can do deposition of very thin layer. So that is where thermal spray technique comes in. So with a little deposition, you can enhance the overall efficiency of an electrolyzer. Otherwise, you have to have a bulk material or use other technique which may not sustain a long life. And then that is where the cost comes in. So you have to look into which technique with less use of the material. Because in electrolysis, you're talking about the surface, the water, the feedstock interacting with the catalyst surface. So you have to protect that one before you think about the substrate itself. Yes. So if you can play with the surface and selection of the right material, the right microstructure of the surface itself, then the rest of the things is secondary.
And you noted leakage as one of the main sort of associated risks with using hydrogen. What other risks do you think that are maybe under discussed or aren't really developed that a lot of these processes that we're discussing today would be able to overcome?
Yeah, well, one of the things which I understand, in my opinion, is if you go for a pressure vessel testing certification, normally they use nitrogen to test it. Nitrogen molecule is bigger than the hydrogen molecule. So nitrogen is used, but they may be using the pressure vessel to store hydrogen. So I think a method is required where you use hydrogen to test the leakage to certify the pressure vessel for hydrogen application. That is one thing. Then, because hydrogen is very light, it can disperse 3 times quicker than the other hydrocarbon. So we need to have an advanced sensing technique which is sensitive enough to detect if the leakage is happening. Yes. Now, if you're looking into lightweight composite cylinder, how you will manufacture those cylinder, if the leakage will happen or not, the safety of those, these are some of the things which not much work has been done. So in my opinion, over next few years, a lot of investment will be happening in these areas about the condition monitoring, structural integrity of the pressure vessel itself, in particular the lightweight, maybe for offshore application, maybe for aerospace application. We don't know. all opportunities are there.
Great, and I think one of the key things you know there is that there are these issues, but there is sort of tangible ways that we can overcome them to develop hydrogen as this sort of widely used energy medium. So I just want to double check, see if there's any more questions in either the chat box or Q&A. And no, I think we're okay. So I think we'll finish up a few minutes early. So I just wanted to take this chance to thank everyone for joining us today for what I thought was a really interesting presentation and discussion. If you do have any more questions or wish to contact us after the event, please do get in touch. I know that Faisal is always open to discussing these further opportunities further and getting the discussion going more. So the recording of today's webinar will be available hopefully in the next week or so on the RGU Knowledge Bites for Business webpage. And I'll take this opportunity to wish you all the best for the rest of your day.